We are beginning a study of how equilibrium is used to better understand acids and bases. First, we need some definitions. Early definitions usually referred to taste. An acid is sour and a base is bitter. Taste is one of the characteristics chemists used. But taste leads to some problems, like early death. So we have begun to better understand the nature of matter. We have developed new definitions. In the late 1800s, early 1900s, Arrhenius proposed that an acid is a substance that, when dissolved in water, increases the hydrogen ion concentration. A base is a substance that, when dissolved in water, increases the concentration of hydroxide ions. What are the limitations of this theory? What is the solvent you must use? It's water. What are the only species that are acid and base? Hydrogen ion and hydroxide ion. So a few years later, Bronsted and Lowry proposed a new definition based upon further exploration of the nature of acids and bases. An acid is a proton donor. Now, not only is the hydrogen ion a proton, or a proton and acid, so also is something like ammonium ion. Any substance that has a removable or acidic proton may be an acid. A base is a proton acceptor. So hydroxide ion is a base because it can accept a proton to become water. And ammonia can accept a proton to become an ammonium ion. So this expanded the definition to include more species or types of chemicals. So, what is a removable proton or acidic proton? Let's look at the ammonium ion. It helps to draw the Lewis structure. Ammonium has 4 available hydrogen atoms. Any one of those can be donated to a base, and the result is stable ammonia. In organic molecules, hydrogens attached to carbon are not easily removed, but a carbon attached to oxygen can be removed. In acetic acid, which is in the second equation, the hydrogen on the end of the COOH can be removed and it forms the acetate ion. And in the last example, which is an alcohol, the hydrogen at the end can be removed, although it is not removed easily. It has the potential, under the right conditions, to be removed. A Bronsted-Lowry base must have a pair of non-bonding electrons. What does that mean? We go back to the Lewis structures, and let's look at hydroxide ion. Draw the non-bonding electrons in the Lewis structure, and any one of the pairs can be used to attract a proton. The nitrogen on ammonia has a lone pair of electrons that will attract a proton. The oxygen on water has a lone pair of electrons that will attract a proton. So there's many different kinds of Bronsted-Lowry bases. But every system has limitations. Bronsted-Lowry provided a very good framework for working with acids and bases in aqueous systems. Remember, we are trying to describe nature, so sometimes things do not fit in boxes. Some substances can be either an acid or a base, for instance, bicarbonate ion. the HCO3 has an ionizable or removable proton. Thus, it can be an acid. It can also accept a proton. Thus, it can act as a base. This kind of substance that acts as an acid or a base is amphiprotic. Bisulfate is an amphiprotic species in water, as is water. Water can act as an acid or a base. So what happens when an acid dissolves in water? The oxygen on the water attracts the hydrogen on fluoride, forming the hydronium ion in fluoride. And if you notice, the HF forms a base. The water, which was a base, forms an acid. And this leads to conjugate acids and bases. Any reaction between an acid and base leads to the formation of a conjugate pair. The acid forms the conjugate base, and the base forms the conjugate acid. You will need to learn to recognize these resulting pairs. You can recognize an acid by identifying the removable or ionizing hydrogen atom. These are some of the common acids you should recognize, the name and the formulas. The base you can recognize because it often has a hydroxide ion group, the OH-, but some are like ammonia and have a lone pair of electrons. So the Bronsted-Lowry is not the latest definition of acid-base systems. It's the one we will use most often. Later, we will look at Lewis acids and bases.